I'm going to be telling you about our finding that pessimism about unknown unknowns inspires conservatism. The problem that we were looking to solve is that a slightly misspecified goal could lead an advanced agent to create an unprecedentedly bad outcome, depending on the environment in which it is operating. And our solution to it is to design an agent which avoids causing unprecedented events. So, our agent is pessimistic. And what that means is it maintains posterior distribution over a countable set of world models. Then it takes, every time it acts, it takes the top however many world models in its posterior until the sum of their posterior weights exceeds beta. Then it acts to maximize the minimum over that set of world models of the expected future discounted reward. Finally, if the pessimistic value of every policy is 0, then it defers action selection to a mentor. So, the setup for our agent, the context in which it is working, it's a reinforcement learner. It is given an observation and a reward after each action. The agent can defer action selection to a mentor, as I mentioned. And the agent is parameterized by the set of world models that it believes possible, that is countable, and its pessimism, which is a number between 0 and 1. So our key results, which I'll describe in words, and then I'll get into one of them in math. Key results, the query probability, the probability that it defers action selection to a mentor, it goes to 0 with probability 1. The value of the agent's policy approaches at least that of the value of the mentor's policy, again, with probability 1. And the main safety result, which takes a little bit of time to describe. For any complexity class, C, we can set M, the set of world models, so that for any event E in the class C, that's a real world event that can be recognized in some complexity. For any such event, we can set beta, the pessimism, so that with arbitrarily high probability, the following holds. For the whole lifetime of the agent, if the event E has never happened before, the agent will not make it happen. Either the mentor will take an action on the agent's behalf, which makes E happen for the first time, or E will never happen. So we call this the probably respecting precedent theorem, the precedent being that E has never happened. And the agent will not unilaterally take an action that makes it happen for the first time. It will only ever defer to the mentor, and the mentor may make it happen for the first time. So I will be introducing enough notation to show you the proper definition of the agent, and then the exact form of the probably respecting precedent theorem. So, the notation. A, O, and R are the sets of actions, observations, and rewards, rewards being between 0 and 1. And these will be regarding the agent's world model and policy. H is the set of interactions that can occur in a time step, so that includes the action, observation, and reward. We denote the action A sub t, the whole time step H sub t. And then H less than t is the entire history, the entire interaction history up until time t. So a policy in general can depend on that whole interaction history. And it can be stochastic in outputting an action. A world model depends on a finite interaction history that ends in an action, and it, again, can be stochastic in outputting an observation and reward. So, P pi nu is how we denote the probability over outcomes when actions are sampled from pi and observations and rewards are sampled from nu. Gamma is the discount factor between 0 and 1. And then the value of a policy in a world model from a particular interaction history is the normalized, so it's between 0 and 1, expected sum of future discounted reward. And that's conditioned on what's been seen so far. So that just means the expectation with respect to p pi nu. Mu denotes the true environment, and I'll remind you of the meaning of all these symbols when they appear. Mu denotes the true environment, and m the countable set of world models considered possible. Pi m denotes the mentor's policy, and p the countable set of mentor models considered possible. And then we assume, for our results, that m and p both contain the truth. Okay, defining the pessimistic agent. This is how we denote the prior weight on world models and mentor models, and these will be strictly positive, which is doable since there's only countably many. This is the posterior on a world model. It's what you'd expect. Nothing surprising there. It's proportional to the prior and the probability assigned to the actual observations and rewards. Qt indicates whether a mentor is queried at time t. And again, the posterior on mentor models is nothing special. It's just you have to note that you only update it when the mentor is in fact queried. Otherwise, you're not observing the mentor. So beta is the agent's pessimism. And then now finally getting into something interesting. M beta t, these are the top world models by posterior weight, given the interaction history so far, until the sum of those posterior weights exceeds beta. So in fact, this depends on the whole interaction history, not just the time. Then the beta pessimistic policy is the argmax over policies where ties are broken arbitrarily, of the minimum over world models in that set of the value of such a policy in such a world model. And this policy that gets chosen will change at every time step, potentially. Okay. So far, there isn't enough of a motive for the agent to explore. Indeed, pessimism discourages novelty, as we'll find in a moment. And so it needs some extra motivation to defer to the mentor so that we can be sure it will end up doing at least as well as the mentor. So the way we calculate the exploration or the probability of deferring to the mentor, the query probability, is as follows. First, we make a Thompson sampled estimate of the value. So pi is sampled from the posterior over mentor models and nu from the posterior over world models. And then we look at the value of that policy in that world model. Yt is the optimal beta pessimistic value, which pi beta maximizes. Then Zt is an IID positive random variable such that there's positive probability of being arbitrarily close to 0. Finally, the enlightened pessimistic policy, which includes some extra deference to the mentor, is that if xt exceeds yt plus zt, or if yt equals 0, then it defers to the mentor. Otherwise, it follows the beta pessimistic policy. Okay, so that's the definition of the agent. Some extra notation for getting into the safety results. F and G are sets of functions. And now we will define a couple complexity classes. CFG, very general complexity class, is just time of F intersect space of G. So if we set F to be the set of polynomial functions and G the set of all functions, that would just be the complexity class P. So a set of strings S has that complexity. That is to say, it's in the complexity class. if there exist functions f and g such that a program can identify whether a string s is in S in at most time depending on f of the length of S and space, that is g of the length of S. The other complexity class we'll make use of is a complexity class over world models. So a world model nu is in the complexity class FCFG if there exists a world model such that given an infinite action sequence and an infinite random bits, it outputs an infinite sequence of observations and rewards distributed according to nu. The tth observation and reward are output before the t+1th action is read. And for some f and g, when the tth observation and reward have been output, the runtime is less than f of t and the space used is less than g of t. Finally, an event E is just a subset of interaction histories that end in an action. And we say that the event E happens if the interaction history so far belongs to that set. Then we say that E has happened if some prefix of the interaction history so far belongs to the set E, and we write that as follows. Next, we'll need to construct M more precisely. So far, it's just been a general set. So we let M be the set of world models in that complexity class. That is to say, it is the complexity class. And the requirements on f and g are that they be closed under addition and that f contains big O of t. These are functions of t. So, probably respecting precedent theorem. If an event E is in that complexity class, and this just means that we divide every function in f by t. For an event in that complexity class, the following happens with high probability. Note that this is the probability, the true probability, because this is how actions are actually sampled, and this is how observations and rewards are actually sampled, mu being the true environment. And as beta goes to 1, this goes to 1 because CE is positive, as appears in the proof, and the prior on the true environment is also strictly positive. So, what happens with high probability? For all t, for the agent's whole lifetime, if the event E has not happened before, then it doesn't happen now, or the mentor is queried. If the mentor is queried, then maybe it does happen now. But if the mentor is not queried, then it definitely does not happen now. E, that is. I'll leave that up for a second. So, this agent is not tractable, unfortunately. That was never the goal of the project. But whereas much of RL attempts to approximate Bayes' optimal reasoning tractably, pessimism is an alternative ideal to Bayes' optimal reasoning. Bayes' optimal sounds pretty good. Why would we ever want something else? Well, what if we couldn't encode an objective that captures every possible failure mode? Then Bayes' optimality with respect to that objective is potentially quite flawed. So if we find ourselves in such a position where we're not confident that our objective captures everything we care about, that is to say, almost every circumstance, especially when agents are acting in ways that have consequences to the world, if we find ourselves in one of these positions, we might rather attempt to tractably approximate pessimism than Bayes' optimality. So in conclusion, pessimists probably respect precedence, and we can exploit this to avoid critical failure even when we can't define it. Thank you.